All right, and I'm going to go to our application, the shared screen. And on this page, just to show where I'm getting this from, on our main page under lecture notes, okay, this is what comes up on the lecture notes. Now, keep in mind, we're using XYZ and not MyMathLab, so the chapters may be a little bit different. In the MyMathLab course, it was chapter 6, but in this course, it's chapter 2. But we're going to talk about the DISC method, and I've provided an applet that shows what a solid of revolution is. So if you take a look at this DISC method, basically we have some curve or some function, and we take that function and we rotate it, in this case, about the x-axis. When you rotate it about the x-axis, it forms what's called a solid of revolution. So notice that both of these curves are being rotated about the x-axis, and they form what are called solids of revolution. When you're dealing with a solid of revolution, there's two ways you can find the volume. You can either use the DISC method, or you can use the shell method. So here I have another applet, and I didn't create these, I sort of taken these online. And it shows that a solid of revolution is created by using a shell method. Okay. If we go back to the DISC method, if you notice here, here's the formula. The volume is equal to the integral from a to b for a of x dx, where a of x is actually the area. If you pay close attention to the DISC method, when you take, in this case, when we take a curve and when we rotate it about the x-axis, it forms a circular disc. We then take the area for that circular disc and we add up all of the area from A to B, and that would give us the volume. So the volume is equal to the integral from A to B for pi times the radius squared dx, where the radius is your function. So we simply, if we're using the DISC method, we would simply stick our function in as a radius, we would square it, we would multiply by pi, and then we would integrate from A to B. Now, when you're using the DISC method, it depends whether you're revolving your solid of revolution about the x-axis or whether you're revolving your solid of revolution about the y-axis. If you're revolving about the x-axis, here are the stipulations. The equation must be expressed in terms of x. Okay, we're going to talk about what that means in a second. The limits of integration are also on the x-axis. Once you have these two conditions satisfied, then you'll use the DISC method. If you're revolving about the y-axis and you're using the DISC method, the equation must be expressed in terms of y. The limits of integration are also on y. Then you'll be able to use the DISC method formula. If you're using the shell method, right, notice that this is the formula for volume. The volume is equal to the integral from A to B for 2 times pi times the shell's radius. The shell's radius is usually x or y times the shell's height, which is generally your function, dx. So notice that the formula for using the shell method and the formula for the DISC method are different. Also, the stipulations are different. if you're using the cylindrical shell method and you're revolving about the x-axis, your equation must be expressed in terms of y, right? And this is a little bit different than the disk method, right? If you're using the disk method, you're rotating about the x-axis, your equation must be expressed in terms of x. If you're using the cylindrical shell method and you're revolving about the x-axis, the equation must be expressed in terms of y. Okay, so notice that it all depends upon which axes you're rotating your solid of revolution around, and it also depends upon which method you're using. Okay, so if you're using the cylindrical shell method about the x-axis, your equation must be expressed in terms of y. The limits of integration are also on the y-axis, and then you have the conditions met to use the shell method. If you're revolving about the y-axis, then your equation must be expressed in terms of x. The limits of integration are also on x, and then you can use the shell method. Now, before we go on any further, let's see what it means to express an equation in terms of x, and what does it mean to express an equation in terms of y. All right, so here's what that means. Okay, so we have this function which is 2x plus 3y is equal to 9. Okay, so I'm just sort of making this function up, right? This is a linear equation in two variables, right? An x and a y variable. How would we express in terms of x? So what does that mean? To express this function in terms of x, in a nutshell, that simply means to solve it for y. Right? So if I wanted to express this in terms of x, I would basically solve it for y. So I would subtract 2x from both sides. I would divide both sides by 3. And we have our function expressed in terms of x. Now I'm going to take the same function and we're going to express in terms of y. So in a nutshell, to express something in terms of y simply means to solve for x. So if I wanted to solve this for x, I would subtract 3y from both sides. And then I would divide by 2. And we have expressed this function in terms of y. All right, so this is what it means to express in terms of x, and this is what it means to express in terms of y. Okay. All right, so I'm going to go back to the shared screen. Okay, this is where I am. All right, so in these problems, there's just one thing. Notice that we're asked to find the volume But in most of the problems, you're not given a method. You're not given the disk method. You're not given the shell method. So as we kind of just look at the problems visually, the first one says find the volume of a solid obtained by rotating about the y-axis, the region bounded by y is equal to 10x squared minus x cubed, and y equal to 0. This gives us a hint. It says a typical shell. So on this very first problem, we would use the shell method. Notice that for the second problem, okay, here again, we're asked to find the volume, but it doesn't give a method. It doesn't tell us whether to use the shell method or whether to use the disk method. The method that you use is based upon how your problem is expressed. It's also based upon the limits. Okay, so we're going to take these one at a time. Right, I'm going to go back to the very first problem. Okay, and we're going to take a look at finding the volume by using the shell method. So remember that the shell method was the volume is equal to the integral from a to b for 2 pi times the shell's radius The shell's radius is usually x or y. Times the shell's height. And the shell's height is usually the function. And we're looking at dx. Okay. Right? Because if you think about a shell, so I'm going to make a sketch over here. And I'm going to go back to the problem for just 1 second. And if you rotate a shell about the y-axis, okay, so here's how this sort of works. So I have a shell. So let's just say I'm going to arbitrarily just draw a point here. If I'm looking at a shell, I'm going to have a radius, right? So the radius is going to depend upon the value for x. We also have a height. And I'm going to see if I can draw this. All right. So this is the height, which is generally the function. So what we're actually doing is we're taking or we're finding the area for each shell from 0 to x, or in this case from a to b. We're finding all of those areas. We're adding up all of the areas, and that gives us a volume. So the radius of the shell is going to depend upon x or y, all depending upon which axis you're rotating about. The shell's height is the function. Okay. So if you've looked at the viewing example, they sort of written this thing out like this. So v is equal to the integral from a to b for 2 pi times x times f of x dx. All right, so you need to know your limits and you need to know the function. Okay. All right, so let's take a look at our problem. So we're given I'm going to switch screens here for a second. All right, we're given the function y is equal to 10x squared minus x cubed, and we're rotating this about the y-axis. We're taking this function, rotating about the y-axis, and y equals to 0. Okay. So in order to get a visual or physical representation, I'm actually going to graph this function. Right. So I'm going to just clear out my home screen. I'm going to clear out my graph, and I'm going to put in the function 10x squared minus x cubed, and I'm going to graph. I'm going to use zoom and 6. Okay, so now I'm going to use zoom and 0. So what zoom 0 does is it should fit the graph to our screen. All right. All right, so in a nutshell, this is what the graph looks like. So we want to take 10x squared minus x cubed. We want to rotate this about y equals to 0. So keep in mind that y equals to 0 is here. So we want this in the first quadrant. Right. So which brings us to a second point. We want the limits of integration from a to b. So I have the function 10x squared minus x cubed. So how do we find the limits from a to b? Well, there are a couple of ways to find the limits. So we have y is equal to 10x squared minus x cubed. And the first thing we're going to do is find the limits. All right, so how do I find the limits? Well, in order to find the limits, we're going to take our equation, 10x squared minus x cubed. We're going to set it equal to 0 and solve for x. Right, so in order to solve this for 0, I'm going to factor out the greatest common factor, which is x squared. Right, so if I factor out x squared, right, I have x squared times the quantity 10 minus x equal to 0. Okay, now I'm going to use the 0 factor property. Right, I'm going to set every factor equal to 0. So I'm going to set x squared equal to 0. I'm going to set 10 minus x equal to 0, and I'm going to solve. So x squared equal to 0. We can take the square root of both sides. So 0 is neither positive nor negative, so x is equal to 0. So 0 is one of our limits. I'm going to solve this for x. I'm going to subtract 10 from both sides. I'm going to multiply both sides by a negative, so I have x is equal to 10. So my limits of integration are from 0 to 10. All right, so I think that we have everything that we need, right? So just to double check, I'm going to go back to the application screen for just 1 second. Right, we're rotating about the y-axis using the shell method. Right, so here we have the shell method. We are rotating about the y-axis, so our equation must be expressed in terms of x. And our equation was 10x squared minus x cubed, so this condition is satisfied. The limits or integration are on the x-axis. Right, so notice that we found the limits of integration are from 0 to 10. So now we're going to set up our volume function using the shell method. So we have the volume is equal to the integral from 0 to 10 for 2 times pi times x. So remember that this is the shell's radius times the shell's height, which is the function. And our function was 10x squared minus x cubed dx. All right, so this was the radius, and this was the shell's height. Okay. So now we'll integrate it. Now, we're going to use the calculator to make the integration or the math on this a little bit less complicated. Okay, but initially this is our setup. We have the integral from 0 to 10 for 2 pi times x times 10x squared minus x cubed. Okay. So now I'm going to use the calculator to actually evaluate this. Now, since our answer calls for a pi in the answer, if the question wants the exact value, you must express pi as pi. Right. So I'm going to do this first calculation. I'm actually going to pull pi in front of the integral operator. Okay, now you don't have to do this in all problems, but for this first example, I'm going to pull pi in front of the integral operator. This is what I'm going to put into the calculator. And then in the end, I'm simply going to reattach pi. All right, so to show how that is done, all right, so there's some things here to answer. It says a typical shell has a radius of x, the circumference is 2 pi x, and they want the shell's height. So notice that the height of the shell is basically our function. That's 10x squared minus x to the third power all right, so we're going to find the volume by using the shell formula. So that's 2 times pi. I want to put the shell's radius. I'm just going to put that in a set of parentheses. I'm also going to put the function in a set of parentheses. So A is going to be 10. All right, because we're integrating this from 0 to 10, right? So they gave us 0. I know in the formula it says from A to B, but they've given us 0, and we found the upper limit is 10. Now I'm going to use the calculator to integrate it. All right, so keep in mind that in our function, we have 10x squared minus x cubed as y sub 1. So I'm going to recall that as y sub 1. So we're going to integrate. So I'm going to go into math. I'm going to scroll either up or down until I get to function integration. I'm going to put in 2x. I'm going to put in a function. So instead of me putting in 10x squared minus x cubed, I'm going to recall that by hitting variables. I want to scroll over to y variables. I want the function, and the function that we want is y sub 1. All right, so this is 2 times x times the function. You have to put in a comma. We have to put in a variable of integration from 0 to 10. And now if we integrate, we get 10,000. So notice we pull pi in front of the integral operator, so we have 10,000 pi. Right, so notice in this problem, we were given a hint as to which method to use. All right. Now for the second problem, all right, notice that there is no method to use. We're simply asked to find the volume. So here it says find the volume of the solid obtained by rotating the region in the first quadrant by the given curve about the y-axis, and we're asked to round exactly to 2 decimal places. And we're given y is equal to 1 minus the quantity x minus 9 squared. Now, which method do we use? Well, the method that you use, it depends upon a couple things. It depends upon how the equation is expressed and the limits. So from what we talked about earlier, notice that this equation is expressed in terms of x. So I'm going to graph it just to see what graph is produced when we graph 1 minus the quantity x minus 9 squared. So I'm going to go into y equals. I'm going to clear out y sub 1. I'm going to put in 1 minus the quantity x minus 9 squared. I'm going to use zoom and 6 to graph. All right, so notice our graph. So notice it's sort of cut off a little bit, so I'm going to go into Windows, and I want to change my x max to 20. Okay, and that should just give me some more room on our x-axis. All right, so notice that our equation is expressed in terms of x. We're rotating this about the y-axis. So I'm going to go back to our disk method and shell method conditions. Okay, here it is. All right, so if we're revolving about the y-axis, right, if you're using the disk method, if you're revolved about the y-axis, your equation must be expressed in terms of y, right? But notice that our equation is expressed in terms of x. If you use the shell method, if you're revolving about the y-axis, your equation must be expressed in terms of x. And our equation, right, 1 minus the quantity x minus 9 squared, that's in terms of x. Our limits of integration are on x. Right, so if we look back at our graph, our limits of integration are from here to here. Okay, so we're going to figure those out. Right. So we're going to use the shell method. Okay. All right, so we have our function, which is expressed in terms of x. We have our limits that are on the x-axis, which we're going to find now. And there's actually two ways to find your limits of integration. And we'll take a look at both of those ways here. All right, so here's the first method. Okay, we have y is equal to one minus x minus 9 quantity square. So in order to find the limits, I can take this equation, 1 minus the quantity x minus 9 squared. We can set that equal to 0 and we can solve. Right, so I can subtract 1 from both sides. I could multiply both sides by a negative, so this will give me x minus 9 quantity squared is equal to 1. I could use the square root property. I could take the square root of both sides. So the side that's squared, the square root and the square cancels. The side that's not squared has to sprout the plus or minus. Now I can solve for x, so I can add 9 to both sides. So I have 9 plus 1, which is 10, and I have 9 minus 1, which is 8. So my limits are 8 and 10. So this is how you can find the limits mathematically. Simply take your equation, set it equal to 0, and solve it. All right, so here's a second method on how to find the limits. Okay, so I'm going to go back to the application screen for just 1 second. I can actually use a calculator, right? Since I have the graph, and I'm going to blow this up slightly. Right, so you may or may not have seen this done before. I'm actually going to go into Zoom, and I want to use Zoom Box. So I'm going to press enter. And notice I have my cursor, and if I move up or down, notice how the cursor moves up or down. What I want to do is I want to put a box around where my equation hits the x-axis. All right, so I'm going to go to a diagonal for my box. I'm going to hit enter. I'm going to drag the box down. I'm going to drag it over. So here's what Zoom Box does. Anything inside of the box, it's going to zoom in on it. So if I hit enter, all right, notice that it just zooms in on the graph. Okay. So you may or may not have to zoom in on your graph. The next thing I want to do is find the two intersection points. Okay. These intersection points are basically the x-intercepts, right? They're where my graph hits the x-axis. The x-intercepts are also called the zeros. So I can find these intercepts by going into calculate. So it's second and calculate. Okay, notice you don't see x-intercept, but you do see 0, and x-intercept and a 0 are one and the same. So I want to hit 0. Now, since we have two intercepts, we have to calculate each one separately. When you're calculating a 0 or an x-intercept, you must set a left bound, you must set a right bound, and you must guess. For left bound, that simply means I must set a point to the left of my 0. Since we're calculating this leftmost intercept first, I'm going to move the cursor somewhere to the left of that 0, and I'm going to hit enter. So notice when you hit enter, it pops up a sideways triangle that should fall to the left of your 0. Now it asks for a right bound. So I'm going to set a point to the right of my 0 or my intercept. I'm going to hit enter, and notice that it popped up another sideways triangle that falls to the right of my 0. For guess, you simply want to hit enter, and it gives you the intercept, which is 8. We can find the other 0 in a similar fashion. I want to go into calculate. I want to calculate the 0. I want to set a left bound. So I'm physically going to set a point to the left of my 0. I want to set a right bound. For guess, I'm going to hit enter. And we have an intercept of 10. Okay, so those are our limits, 8 and 10. Right now we have enough information to set up the volume by using the shell method. So the volume is equal to the integral from 8 to 10 or 2 times pi times the shell's radius, which is x, times the shell's height, which is our function, which is 1 minus the quantity x minus 9 squared dx. All right, and this is what we're going to integrate by using the calculator. Okay, but any questions on how this function is set up? We have our limits. Okay, we found the limits in a couple ways. We found the limits analytically. We also found the limits using the zero function, the calculator, and we were given the function expressed in terms of x. All right, so if we were to put this into the calculator, I'm going to go back to our home screen. So I want to integrate. And here we're asked to round to 2 decimal places. So I'm going to actually put pi in the calculation. So it's 2 times pi. So notice pi is above my caret and it's a second function. So it's 2 times pi times the shell's radius, which is x, times the shell's height, which is the function. And since I have the function stored as y1 on the calculator, I'm going to recall that function by pressing variables. I'm going to scroll over to y variables. We want the function, and we want the function y sub 1, comma, the variable of integration is x. Our lower limit is 8, our upper limit is 10. And we have 79.39, which is 75.40. All right, now I'm actually going to skip down to problem number 5. I believe problem 3 and 4 are using the shell method. Okay, but once we get to problem number 5, so here again, we're asked to find a volume, but we're not given a method to use. So the method that we use is going to be based upon the equation that we're given, how it's expressed, and also the limits. So here we're asked to find the volume of a solid generated by rotating about the x-axis, right? So here we're rotating about the x-axis. The region that's bounded by y is equal to 3.1 raised to the power of x. X is equal to -4 to x is equal to +4. Right? So if we look back at our conditions, we're rotating about the x-axis. Our equation is expressed in terms of x, and we're given the limits on x. All right, so if we look at this method, we are rotating about the x-axis. The equation is expressed in terms of x, and our limits of integration are on the x-axis. So for this problem, we should use the disk method. Okay. So as always, I'm going to graph. 3.1 raised to the power of x. Okay, 3.1 raised to the power of x. I'm going to use Zoom 6 to graph. All right, so notice that this is our graph, and we want to rotate this graph about the x-axis in the region from x is equal to -4 to x is equal to +4. So I believe we have everything we need. We have the function, we have our limits, so we're going to use the dis method. Okay, so I'm going to go back to the camera and actually write that out. All right, so we have the volume is equal to the integral from a to b for pi times the radius squared and our radius is the function. So I'm going to just plug in all that information. So we have the integral from -4 to +4 for pi times the radius, which is our function, and that function was 3.1 raised to the x power squared dx. Right, so this is what we're going to integrate in the calculator. All right, but any questions about the setup for the dis method? Okay, we were given the equation expressed in terms of x, and also the limits are on the x-axis. Okay, so I'm going to go back to the home screen. I'm going to pull up function integration. So remember, the function was pi times the radius squared. So I'm simply going to recall the function squared, comma, x is the variable of integration from -4 to +4. And we have 11,841.22. All right, and we'll take a look at one more, problem number 6. Okay. So here again in problem number 6, there is no method to use, right? We're simply given find the volume, we're given the function. Well, I'll take that back. We're given the function y is equal to sine squared x and y is equal to 0 between 0 and pi about the x-axis. So here we're given the function that's expressed in terms of x We're also given the limits of integration on the x-axis. So here again, we're going to use the dis method. All right, so I'm going to go back to the camera and write this out. So the volume is equal to the integral from A to B for pi times the radius squared dx. So here we have the volume from 0 to pi for pi times the radius, which is our function. So our function was sine squared x squared dx. So this is what we'll put into the calculator. All right, so I'm going to recall the function integration. We're going to put in the function, which is pi times the sine squared. So I want to put in sine x squared, comma x from 0 to pi and I'm sorry, I put that in incorrectly. Let me do that again. So this is function integration. So I think what happened was, I'm going to go to y equals, just so we're correct on this. And I'm going to put this into y equals sine squared x. Okay. So one thing about sine squared x, you can't actually put the square in front of above the sine. Right, you have to put in the argument for sine, and then you want to close off that argument, and then you want to square. So from this point, I'm going to hit zoom 6. And I want to hit zoom 7. So what zoom 7 does is it puts this in a 0, pi over 2, pi, 3 pi over 2, 2 pi range. So notice that we're graphing, or we're actually rotating this from 0 to pi, right? So the limits were given. So now I'm going to put in a function integration for pi times our function. So I'm going to recall our function squared. Okay, so you must take the sine squared and you got to square that again. So I have y sub 1 squared, comma, x is the variable of integration from 0 to pi. And we have 3.7. Okay. So here my mistake was, if you're not using y sub 1, when you put that into the function integration, I'm going to put in the sine of x squared, and then you have to square it again, comma x from 0 to pi. and then you will get 3.7. Okay, so make sure you take your function, which in this case is sine x squared, and then you must square it again. Okay, because this method formula calls for the radius squared. Right. So I believe that this method is used for problem number 7 and for problem number 8. Okay. All right, so I'm going to go back to our document camera. Okay, so I'm going to stop the recording. If I can.